here's one slice right here. You see that one slice?
Yeah. It's just a circle, isn't it?
It's just a circle, yes. Here is one slice. Each of these slices is going to be a circle, absolutely. Each of those. So what is the area of that circle in terms of x? Well, the area of a circle is pi times radius squared, right? In this case, our radius is what?
Y.
Root x.
Yeah.
It is y. No, that's key to remember too. It is y. There are times when we will need to switch our variables, but this is not quite yet. So it is root x. So the area of each of these slices, and I think they used a too, right, for each of our slices before, is going to be pi times root x what?
Squared.
So the area of each of our circles is really just going to be pi times x, correct?
Yeah.
Now here's the thing. That right there, when you find the area of a circle, is that a volume?
No.
No, what is that? A surface area, right? It's a surface area, right?
Dx.
So in order to find the volume of a cylinder, it's pi r squared times the height, right? Think of this going sideways. We need some sort of depth in order to give this thing volume. What is our height / depth going to be?
Dx.
No.
The integral from 0 to
No.
Yeah.
For each of our slices, it's going to be dx.
Okay.
Our leftmost one will start at 0, and our biggest one will go to 2. But the point is, if I just wanted the volume of this slice, we would need to take, so the volume in terms of x is going to be pi x times dx. You need a depth, right? Drawing the picture is really, really helpful because when you're looking at this slice is perpendicular to which axis?
X.
The x-axis. This slice is perpendicular to the x-axis, meaning you have to have dx. Where is the skinny side? The skinny side is parallel to the x-axis, so it has to be dx. This is really important because if it's going to be dx, what are you integrating with respect to?
X.
X. Are there times when you're going to integrate with respect to y?
Yeah.
Absolutely, because we could have rotated this around the y-axis.
That would have been.
It's not that hard. You just have to change the integral a little bit. That's it. But a common mistake is to do the wrong, to integrate with respect to the wrong variable. Don't make the mistake. If you draw this and think to yourself, what am I perpendicular to for the slice? The x, oh, it's dx. So that's the volume of each of the slices. How many of these are we adding up? So we're integrating from 0 to 2 of pi x dx. That's it. So that's just pi integral from 0 to 2 of x dx. And then that was that about as straightforward as it gets?
Yeah.
Yeah, that's pi times 1 over 2 from 0 to 2. So that's going to be pi over 2 x squared 0 to 2, which is just going to be what? 4 pi over 2, which is 2 pi, right? You plug in 0 at 0. That's it. That's it. Now here's the thing. The key. Make your sketch and make sure you are integrating with respect to the right thing. So let's just change this a little tiny bit, okay? Let's say I said, okay, f of x is the square root of x. And let's say g of x is 1/2 the square root of x. And we're going from x equals 0 to say x equals 2. Same thing. And we're going to rotate around the x-axis. What's our first step? Draw it. Well, do we know what the square root of x looks like?
Yep.
Yeah, sure. We'll make this red, so it's going to be something like, I don't know, like that, right? So if that's the square root of x and we're rotating around the x-axis, it's going to go down like that, correct? 1/2 the square root of x, what's that going to look like?
It's going to look like
Yeah, it's going to look like this and
that.
that's, I almost did it. Okay, it's not the best, but I'm doing the best I can here. Like this, right? Okay, and if we spin these things, what happens? You end up with, let's draw one slice here. There's that one, right? And then you have, each of our slices looks like what?
A circle.
Kind of.
Like a washer.
It's a washer. What's the, this is functionally identical to what we just did, except what are we going to be doing? We're subtracting the middle, right? So you can do this as two integrals. You can do this as two integrals. So let's just look at what this would be separately. We know that the outer one is the integral from 0 to 2 of pi times what? Pi x dx. Is that correct?
Yeah.
Minus the integral from 0 to 2 of pi times what? It's x over what? Why is it x over 4? Yeah, so what you're doing there, I'll just write this out. You had 1/2 root x squared dx. Is that okay? And this one right here, if we wanted to start the absolute beginning, is this. Does everybody agree with that?
Yeah.
Let's just put this together a little bit. What's in both that we could factor out of both?
Pi.
You could factor out a pi, correct? So you'd have pi times the integral from 0 to 2 of this squared dx, right? Minus the integral from 0 to 2 of, well, I'm intentionally not writing it out so we can see what's going on. Is that okay?
Mm-hmm.
Now, we have the same limits of integration, right? In each one. So what can we write this as? Pi times 0 to 2 of what? Minus what? 1/2 root x squared dx, right? When you're looking at this, let's think of this as, if this is a washer, we're going to call the distance from here to here capital R, and the distance from here to here little r. There's going to be an outer and there's going to be an inner, right? So if we generalize this, you're going to have pi times the integral from 0 to 2 of what? Big R squared minus little r squared dx, right? And let's go even further. Do we have to go from 0 to 2?
No.
If we were going to generalize this, it wouldn't go from 0 to 2. It would go from A to B. Here's the generalized washer format. A washer is just a disc with the center cut out. And the center is going to be also going to be a disc. So whenever you see a washer, it's really just two circles. Do you have to do it separately? No. Could this simplify really nicely and collapse really nicely?
Yeah.
Absolutely. But again, remember, capital R is the outer one and the little one is little r, right? Theoretically, could they switch?
Yeah.
And if they switch, you just have to do it as separate integrals, right? Does that make sense, everybody?
Yeah.
Absolutely. So let's do one of these.
So you just have to find the point of
And what's the highest y value? You're scanning from 0 to 4, and what's it going to be? It's going to be pi times, just remember this, it's the radius squared dy, right? We haven't solved for y. Just do it in
I have
pieces.
a question.
We're not, hold on. Do we know what the radius is?
Yes.
We do. Does it have to be in terms of x or y? Y. We're integrating with respect to y.
Over.
We're integrating with respect to y, correct?
dy.
So we need this distance, right? We need that distance.
Yeah.
Each of these points is what? You go over x and then you go up
Y. R squared
x cubed,
x cubed.
right?
Yes.
Is that correct? So theoretically, you could plug in x, right? But is that what we need? Are we integrating? No, we're integrating with respect to
R.
y.
R.
Y. Y. Stay with that, everybody. You're anchored y, right? We know that y is equal to what? X cubed, right? What does x equal? Cube root of y. We wanted x, but we wanted x in terms of what?
Y.
Y. So what's our integral going to be? 0 to 4, pull the pi out, and you're going to be squaring what? The cube root of y. That's correct. There it is. That's it. And can you integrate that? Yes. Here's the thing. This is key. Once you decide what you're integrating with respect to, you have to write everything else
In terms
of that variable. You can't integrate this. This is not something you do in this class. We are doing single variable calculus. We're not doing multivariable calculus. Are you going to do things like that all the time in multi? Yes. And is it that hard? Not really. But that's not what we're doing on this question right here. So could you finish that right there?
Yeah.
Okay, so we have y equals x to the 2/3. X equals 1. What does x to the 2/3 mean? That's the cube root of x squared, right? Is that concave up or concave? What is that? Do you remember what it is?
Down.
It's concave down? Is it concave up?
Concave down.
I think it's concave down, right?
It's never negative.
But it's never negative. I agree. Well, no, it can be negative because you can take the... Oh, no, because you're squaring it, right? Yeah. So what's this thing going to look like? It's going to be... Looks like this, right? Does it look like that? Okay. And we go to x equals... and y equals 0. So our bottom boundary is the x-axis. So that we're taking that shape, and what are we rotating it around?
The y-axis.
The y-axis. So if we do this, it goes up 3, right? So it goes up like this, right? That was not quite the best. Just do the best you can. It's fine. So it kind of looks like this, right? And what is each of our slices going to look like? Here we go. Let's see if I can do this here. So I'm going to do this to here. Actually, I'm going to do a higher one. Let's do here to here. So let's say...
Oh. It's a dip.
Do you see the washer?
Yeah.
Yeah.
Everybody see it? Now you can do that, and some people actually do this too. They draw this right here.
Height.
They draw the little height there, right? Is that okay? Give it a little three-dimensionality.
Mm-hmm.
So this little distance right here, this
dy.
distance right here, what is that?
dy.
That is dy. So you are integrating with respect to
Y.
absolutely here. So what's the lower bound?
Um,
What's the lowest you can make this slice? 0, right? How do you figure out what the highest is? You need to know what that is, right?
Plug in x equals 1.
What is x? What's 1 to the 2/3?
1.
1, yeah. So it's 1, right? Okay, and we knew it was pi times the outer radius squared minus what?
The inner radius.
The inner radius squared, and it's going to be dy. Do you agree with that? So our big R and our little r must be in terms of what?
Y.
Can someone tell me which radius is the much easier one to write?
Probably the big one.
Why?
X equals
Because
1.
It's always 1.
One.
It's always 1. The big radius stays at 1. Do you agree with that, everybody?
Yeah.
So let's just do this one at a time. 0 to 1 of 1 squared minus little r squared dy. Is that correct?
Yeah.
So little r, where is little r? It's right there. That's our little r, correct? And at that point, it's y equals what? X to the 2/3. But we need, so we want the x value. We want to go over x, right? But we need it in terms of y. So what do we need to solve for? What does that mean?
Y equals
X equals what? Y to the
3/2.
3/2. Exactly. You take this, and you end up with pi 0 to 1 of 1 minus y to the 3/2 dy. Is that something you can definitely solve?
Most definitely.
Absolutely. I mean, I'll simplify it a little bit. You end up with 1 minus y cubed dy. Is that generally about as easy as it comes?
Probably.
Absolutely. It's generally speaking about as easy as it comes. And that's it, everybody.
I have a question.
That's it. You can set these up. You can knock these things back as long as you sketch. There's no hole in this, right? Are we going to be integrating with respect to x or y?
1.
Y. You can see that because the slice is perpendicular to the
X-axis.
y-axis. It's perpendicular to the y-axis, so it's dy. Correct?
Parallel.
Now, here's the thing. What can you tell me about this shape? What's one interesting, useful thing you can tell me about this shape? It is symmetric, right? It's symmetric over the x-axis, right? So instead of doing from the bottom to the top, we can go from...
We can go from 1 to 0, 0 to 1.
Remember, we're integrating from bottom to top. So instead of going from the bottom to the top... Thank you. Go from 0 to the top. So it's 0. And what's the top of this thing? 1. It's x equals 1. What's 1 squared?
1.
1. So it goes from 0 to... We're just doubling it. Are we okay with that?
Yeah.
Okay, so our radius, everybody, our radius is this distance right there. That is our radius.
This actually is a cylinder.
That is our radius.
Cylinder. Sphere.
It is not a sphere. It is absolutely not a sphere. It is not differentiable there. Therefore, it is not a sphere.
Okay.
It is not.
Okay.
Because the derivative changes instantaneously. So therefore, at these 2 points right here, it's positive and it changes instantaneously to negative.
Okay. So the
Right?
slope is never. You're right. Yeah.
It changes, right?
I
Okay.
get it.
It never goes through 0, right? Exactly. So in this case, you guys did really well, by the way, on identifying if the mean value theorem was applicable, but your other stuff was surprisingly strange. So on this, maybe if I feel like it, we need that radius right there, and doesn't need to be in terms of x or y. So we know it's pi, and it's just r squared, correct? But we need that r value in terms of y.
Y, so y squared.
So we know that what? We know that y is equal to
Root r, root x.
root x. Do you agree with that?
Yeah.
Yeah.
Y is equal to root x.
We already gave us this one.
But we need this distance right here. How do you get the distance between A and B? If you had A to B, if you had B here and A here, how do you get the distance from A to B? A minus B. A minus B. Exactly. So can you tell me what the distance is from here to here? 1 minus what? It's not r. Stop saying r.
Minus x.
R is what we're trying to get. R is what we're trying to get. Root x? So it's 1 minus, it would be, initially, r would be 1 minus x, right? Do you agree with that? But we don't want it in terms of x. What do we want?
In terms of
Oh, we didn't even need to do that. It was already done for us, right? So what's it going to be? R is equal to 1 minus.
y squared.
So what do you have here? 2 pi, the integral from
0 to 1.
0 to 1 of
1 minus
y squared squared dy. Can you do that?
Yeah.
What do you have to do first?
Uh,
You have to square it. You have to multiply it out, distribute, multiply it out, right? And then you're done. Okay. Okay, so